Assalamu alaikum class. Bismillahirrahmanirrahim. Lecture 8, your course Statistical Inference 1, and that will be held, this lecture will be held on 9th of January. Topic that will be under consideration of this lecture 8, maximum likelihood and minimum variance and efficiency. Then successive approximation to maximum likelihood estimators, and some examples we will consider relating to this topic, and then maximum likelihood estimators for several parameters, the case of joint efficiency, and also consistency and efficiency in the general multi parameters, and we will consider the examples relating to this. The topic first, that is maximum likelihood, minimum variance and sufficiency, is and we know is an alternative to the minimum variance and biased estimator. For many estimation problems, the minimum variance and biased estimator does not exist. Moreover, when it does exist, there is no systematic procedure for finding it. In contrast, the maximum likelihood does not necessarily satisfy any optimality criterion, but it can almost always be computed, either through exact formulations or numerical techniques. For this reason, the maximum likelihood estimator is one of the most common estimation procedures used in practice. The maximum likelihood estimator is an important type of estimator for the following reason, that it implements the likelihood principles. It is often simple and easy to compute, and asymptotic optimality properties it holds for consistency and efficiency, and also invariant under parameterizations. If any efficient estimator exists, it is the maximum likelihood estimator. So we have seen in the previous chapters that when this is a single sufficient statistic, the likelihood function is of the form in which minimum variance and biased estimation of some function of theta is possible. Thus, the maximum likelihood estimation or the function is in the form of curly log of L over curly theta is equal to A of theta and the T minus G of theta. So we will find, for finding the solution, we put this curly log of L over curly theta is equal to 0. And from where we get the value of the statistic G of theta, we call it T. Then we differentiate with respect to, we take its second curly derivative, and then we find out its value, and then putting it again into is equal to the 0, we find out the minimum unbiased estimator of G of theta. So adopting this procedure, we will use the normal distribution and maybe Poisson or binomial distribution. Means we use the continuous distribution as well as the discrete distribution to find out the asymptotic variance of the maximum likelihood estimator of sometimes variance or the standard deviation from a normal distribution or some other distribution. So the procedure will be, first we find the likelihood function, then we find out their log likelihood functions, then we find out their curly derivatives, and we put the values curly derivative first, then its partial second derivative, then we put the values is equal to 0, and we find their expectations, and the way we find out the values of the expected of x square and expected of x whole square, we put into the equation and get the answer. So this procedure we will adopt for the normal distribution or other discrete distribution also. Inshallah, we will see in the class when we have a physics class. So next topic under consideration will be successive approximation to maximum likelihood estimators, and we will solve also some examples relating to this topic from some discrete distribution or some from the continuous distribution. If we see the successive approximation approach to parameter optimization and maximum likelihood estimation, most commonly parameters are estimated on some initial psychologistic estimates derived using a rapid method. Parameters are then held constant during a tree search, and ideally the procedure is repeated until convergence is achieved. So we can say the likelihood equation is so complicated that it cannot be solved explicitly. In that case, we use iterative methods to find the root of the equation. Initially, we start from some trial value t, expanding curly log of L over curly theta in a Taylor series about its value at t. We obtain its derivative at theta is equal to theta hat of first derivative, and then we put the value is equal to 0, and from that we find out the value of the theta hat and t. So if we can close t so that it is likely to be in the neighborhood of theta hat, and we can replace the theta by theta hat and obtain our desired results. So this is the procedure. We will find the approximate maximum likelihood estimator for theta in some continuous distribution like normal distribution, Cauchy distribution, or in some discrete distribution like you can say the binomial distribution, the Poisson distribution, and we also consider a multinomial distribution. We also consider a multinomial distribution with 4 classes, the respective probabilities in the 4 classes, and we will also find out its successive approximation approach to the parameter optimization in maximum likelihood estimation. Or if we move to the its next topic, it will be in the maximum likelihood estimator for several parameters. So maximum likelihood method in parameter estimation is that we assume the value of the parameter are fixed about unknown, and we also assume that best estimate theta hat is obtained by maximizing the probability of obtaining the samples x1, x2 up to xn actually observed, that is training data, and probability of x1, x2 up to xn given theta is equal to probability of d given theta is the parameter estimate of the maximum likelihood estimator. So maximum likelihood estimator for multiple parameters also exist. And for several parameters, we have in the matrix form, if we take it as, then it will be equal to the pi n varying from 1 till n, f of x, xn alpha, or then we put the PDF over here and then find out the value. So if we take x and theta as vectors, the maximum likelihood principle, namely L x of theta is greater than or equal to L of x theta, holds good. We have to close the set of additionable values of the parameters theta 1 up to theta k, which makes the likelihood function an absolute maximum. The necessary condition for a local turning point in the likelihood function is that the likelihood function of Lx of theta 1 up to theta k and its derivative with respect to theta r should be equal to 0. And it should be a sufficient condition that is be maximum is that the matrix of second derivative be a negative definite. The k equations are to be solved for the k maximum likelihood estimators theta 1 up to theta k. So this next topic will be the case of joint sufficiency. So if we see and say that just as in the case of a single sufficient statistic, if there exists a set of S statistic T1 up to Ts, which are jointly sufficient for the parameters theta 1 up to theta k and maximum likelihood estimators theta 1 hat up to theta k hat must be the functions, the sufficient statistic, This follows from the factorization that the likelihood function of x1 theta 1 up to theta k is equal to g of t1 up to ts theta 1 up to theta k h of x. Since h of x does not contain theta 1 up to theta k, however, the maximum likelihood estimators need not be one-to-one functions of the sufficient set of statistics and are therefore not necessarily themselves a sufficient set. In the example, we have already met the cases where the maximum likelihood estimators of a single parameter is a function of only one of the jointly sufficient pair of statistics, there being no single sufficient statistic. So we will generalize the multiple parameter case and find out the values. So if we see the joint sufficient statistic for the Poisson distribution is given in the example in the slide, that is f of x1, x2 up to xn lambda, which will be equal to e power n minus lambda, lambda power sum of xi. If we generalized it for the multiple cases, for the multiple parameters, is into 1 over x1 factorial, x2 factorial up to xn factorial. We take it as h of x 1 x2 up to xn, and it will become the phi of mu sum of xi lambda. Or in the case of normal distribution, it will be equal to the exponents of minus n over 2 x bar minus mu whole square into 1 over 2 pi n over 2 exponents of minus 1 over 2 sum of I varies from 1 till n xi minus x bar whole square. We will make it as h of x, and it will be phi of x. So the last topic will be consistency and efficiency in the general multiple parameter cases, and we will also see some examples relating to this. So in the case of the properties of point estimators, we have seen the good properties of should be unbiasedness, sufficiency, and consistency, because several different sample statistics can be used as a point estimators of the different population parameters. We will use the following general notations during the session for theta as the population parameter and theta head as the sample statistic or the point estimator of the theta. In general, theta represents any population parameter and theta head represents the corresponding sample statistic. So in the general case where there is not necessarily a set of k sufficient statistic for the k parameters, the joint maximum likelihood estimators have similar optimum properties in large samples to those in the single parameter case. Firstly, we will see the general conditions of the joint minimum maximum likelihood estimators, convergence in probability as a set to the true set of the parameter values. And secondly, we will see the joint maximum likelihood estimators turned under regularity conditions to a multivariate normal distribution with dispersion matrix whose inverse will be given by in V of RS, and we will find out if there is a set of k jointly sufficient statistic for the k parameters that we may use to obtain for the inverse of the dispersion matrix of the maximum likelihood estimator in the large cases. We will also see the determinant of the dispersion matrices that we will obtain is also called the generalized variance. Thus, the maximum likelihood estimators minimize the generalized variance in the large samples. So these will be the topic that we will discuss under the maximum likelihood estimators and the method of movements in the class. And inshallah, this it will be more clear to you. This video is, I hope, inshallah, will be helpful to understand the theme relating to the or the concept relating to the topics of the lectures. Till then, Allah Hafiz, and see you inshallah in the class on Sunday. God bless you all.